what I've talked about. So last time I showed you an actual circuit, and now what I'd like to show you is a simulated circuit. So I'm going to build a simulated circuit here. So I've got a switch and some wires. And I'm going to put an ammeter in here. Now when I put in an ammeter, I put it in series because the ammeter is going to measure how much current is moving through the circuit. Then I'll put in a light bulb. Oh, one thing I love about this is it shows you that a light bulb actually has 2 points of contact. One is on the bottom and one is on the side. And the side, because it's a big cylinder, you can touch it anywhere on the side. But the bottom is is your negative terminal, and the top is your positive terminal. And then I'll get another wire there. And then we'll go back to the battery. Now, I don't need to make it look like a rectangle like this. I'm doing it to make it a little bit easier to look at. And now what I'm going to do is I'm going to close the switch. There we go. I close the switch, and we can watch the current travel. The positive terminal of the battery is the copper side. So here we can see the electron flow is counterclockwise coming out of the negative terminal of the battery. I like this little simulation because it shows conventional current, which I talked about yesterday. There's conventional current modeled as positive charge flow. This simulation doesn't actually doesn't actually put the charges in because we know the charges aren't moving, but again, we're modeling that the current, the conventional current itself is traveling clockwise. I can take a voltmeter and I can put a voltmeter across the light bulb if I want to see what voltage I've got running here. So this looks like it's a 9-volt battery and we've got 0.9 amps. And in the, and there's a whole bunch of other stuff that I can put in here, and this is fun to play with. We can play with that in a moment. But let's see. So the next thing I'm going to do is click on the battery, and I'm going to change the voltage, and I want you guys to watch what happens to the current. So now the voltage is 0, and now it's 1.5, and the current is 0.15. And the voltage is 5, and the current is 0.5. And the voltage is 10.5, and the current is 1.05. So hopefully you guys are seeing a relationship between the voltage and the current. The voltage is 10 times the current, no matter what I make it. And you can see that as I increase the voltage and the current speeds up, I don't know how well it's coming through on the Zoom, but the current is now traveling faster. So basically this linear relationship between voltage and current is called Ohm's law. So I'll say that again. This linear relationship between voltage and current is called Ohm's law. And so what I can say here is I can say that the voltage equals the current times the resistance. And let's look at an example here. So 35 volts equals 3.5 amps. So 35 volts is the voltage, 3.5 amps is the current, and then the resistor is the light bulb, and the resistor in this case is 10 ohms. Now, with something like a light bulb, it's hard to tell what the resistance actually is. So, what I'm going to do is I'm going to take the light bulb out, which isn't as much. Ooh, I took the battery out. I'm going to take the light bulb out. The light bulb over there. I'm going to put a battery back in, and I'm going to get a resistor. And I'm going to double click on this resistor, and I have it set to 10 ohms. And so now I know that this resistor is set at 10 ohms. And I'm going to talk about the resistor and these stripes in a little bit. But again, I know the resistance is set at 10 ohms. So if I crank the voltage back up to 35, which was my number, I can see for sure that the voltage across this is 35 volts. The current is 3.5 amps, and the resistance then is 10 ohms, and 3.5 times 10 is 35. And this relationship holds. So the resistor is remaining constant. So I know that the voltage equals the current times 10 ohms. So one more idea, and then let's see what questions you all have. So I could make a graph of voltage versus current. And if I did that, then the slope would be this 10 ohms. So the Ohm's law states that the slope of a voltage versus current graph is the resistance of the circuit. And if we get a straight line, which I didn't draw this very well, I'm struggling with my mouse here. But if we get a straight line, then the substance is said to be ohmic, or to have a linear relationship between voltage and current. Okay, so again, I want to talk a little bit about resistance. So we've seen a light bulb as a resistor. By the way, yesterday, that light bulb, I hooked it up to a very high voltage, or it wasn't very high, but it was more than this light bulb was built for, and you can see the discoloration there is from burning, basically. I also have a very small but not too painful blister on my thumb, which I will spare you the details. So what I'd like to do is talk more about resistance and resistors. So first of all, everything has resistance. There's no wires that have zero resistance. Well, except actually superconductors, which I take it back, but that's for a different day. So in general, in basic circuits, everything has a little bit of resistance, even wires like made out of copper. Now, as you would imagine, I'm just peeking to make sure I say the same thing right here. Copper has one of the best resistances, or one of the lowest resistivities. Silver is even better. Silver is actually the best for conducting electricity. However, silver is expensive. Copper is a little bit cheaper. Gold is very good too. Aluminum is not bad. And for a long time, they used aluminum in homes. My husband and I bought a house in Monona. We don't live in this house anymore. We live in Fitchburg, but when we lived in the Monona house, it was built in 1960, and that was a time when they loved using aluminum for wires. And aluminum is cheap, but because the resistivity is higher, it dissipates more energy and it causes heat. And homes with aluminum wiring are more prone to electrical fires, which is a little scary. So all of this to say that resistivity, one thing that it depends on is what the resistance depends on what you make your wire out of. So there's a variable called resistivity, and it's measured in ohm meters. So another thing about resistance is the longer the wire, the more resistance there is. So I have a couple of old school examples here. This is a very old school piece of lab equipment. And it's basically a bunch of different spools of wire. And the spools are, if you can see here, the spools are different lengths, 10 meters and 20 meters. 4 of the 5 are copper, and 1 of the 5 is nickel, nickel-plated silver, or maybe silver-plated nickel. I don't know. So the length of the wire matters, and the longer that the wire is, the more resistance it has. going to depend on length. And then the third thing that resistance depends on is the gauge of the wire. The gauge of the wire is the thickness. So with these, I hope my camera is not the greatest. I don't know if you can tell, like this middle one, the wire is a bit thicker, and here it's a bit thinner. This is another example of an old school, these are called resistance coils, and they're basically just different lengths of wire made out of different stuff, and they're all different thicknesses. And so the resistance of these coils depends on what it's made out of, depends on the length, and the third thing that it depends on is the cross-sectional area. So we've got resistivity, we've got length, and we've got area. I'm going to show you an example from the notes. This is a little redundant if you watch my videos, but I'm going to go for it anyway. So resistance, again, depends on length, cross-sectional area, and material. And then the formula for the resistance of a substance is the resistivity, which is this lowercase rho. It depends on the material, the length of it, and the area. And what we can see in this chart up above is that if something has more length, it's going to have more resistance. If it has less area, it's going to have more resistance. So that's why we divide by the area. And then if we have, we have the material, the length, and the area. Oh, and temperature, we're just going to assume that we're working at room temperature, but it's also true that if things heat up, they have a higher resistance. Okay. Let's see. What do I want to say next? Oh, yeah. Okay. So next. So if you look at a circuit board, or if somebody's building a circuit board, you'll see all these little round resistors. You can Google this for fun. See all these little resistors that look like this? And I have these in the classroom. Show them here. Here's a little resistor of the type that I would use in a circuit board. And I've got different ones with different colors. And the reason that they're constructed this way is that this is going to get soldered in, so that, that means we're going to take lead solder and actually like pin this into a circuit, and it won't be able to move. If we printed a number on here, and if we printed and the number ended up on the bottom side, I wouldn't know what resistor this is. So by putting colors all the way around it, I can look at the colors and determine what the resistance of this thing actually is. And so here's one that's got different colors and therefore a different resistance. So there's a code for figuring out the colors of a resistor. So let me go back to my notes for a moment. So this is a resistor color table. So the first band is the first digit. The second band is the second digit. So on this resistor here, make this bigger. So on this resistor here, the first band is blue, so that's a 6, and the second band is red, so that's a 2. So this is 62 something. But I don't know if it's 6.2, 62, 620, 6200. I don't know what it is. So the third digit is a multiplier. On this resistor, the color is black, and so the multiplier is just 1. So this resistor, blue, red, black, is just 62 ohms. And then the last color tells me the tolerance. because these resistors are mass produced and they're very, very cheap. And what they do is they take the stuff that the resistor is made out of, whether it's plastic or some kind of ceramic or whatever, and they put it in a big vat and they mix it all around, and then they extrude it to create these resistors. But their process is not perfect. Manufacturing processes are never perfect. So there's a tolerance here, and the tolerance on this one is 5%. So they're telling us this resistor is probably 62 ohms, but we'll guarantee it's within 5% of 62 ohms. So when you're building your circuits, you kind of know. And if you, yeah, you can pay more for better resistors. So let's do another example. So here is a resistor that's got brown, green, black. So brown would be 1, green would be 5, so that's 15. Black is multiplier 1 again, and then we've got a tolerance of, a brown tolerance of 1%. Actually, I think that's gold, and I didn't put that on here, but I think gold is 5%. Okay, I'm going to, again, pause my recording.